So, greetings and good morning. Today we will have two lectures. This is the third lecture of the series after the two we had yesterday. And we talked about the high harmonic generation yesterday, the generation of attosecond pulses and how you get energy augmentation and how you get phase coherence. So, that is what generates the attosecond pulse laser. It is an amazing technology, and no wonder it fetched the Nobel Prize a few months ago. Today we will discuss some applications of this technology today and tomorrow. In the remaining 4 lectures, this is the third lecture, we will discuss some applications and what do you do with these attosecond pulses. So, a major application here is the study of photoionization time delay. Okay. I mentioned yesterday that when photoionization takes place, as in the sense of Einstein's photoelectric effect, a photon is absorbed and the electron is knocked out, and in Einstein's model more than 100 years ago, 1905, which was his magic year, the photoionization was considered to take place instantly. So, there was no delay that was suspected. There was no theoretical tools to predict delay at that time. This was 1905, mind you, this was even before most of quantum mechanics, which came in the 1920s. And of course, there was no experimental techniques available at that time. It always amazes me as to how many things Einstein has contributed to. I mean, even the lasers came from Einstein's work, his Einstein A and B coefficient. Quantum mechanics came out of his interpretation of photoelectric effect, and then other things, of course, in his magic here, including relativity, the special theory, and then 10 years later the general theory of relativity. But what comes out of Einstein's work is also deep questions that he raised about quantum mechanics, about entanglement, the EPR paradox and other things. And we will see how these studies in attosecond physics even take us to some of those questions at a certain level, but I will come to that maybe tomorrow. Now, I would like to begin with this diagram over here. Look at the upper left of this figure here, and over here you have an electron ion collision. An electron collides with an ion, and then you have scattering. This is quantum scattering, and then you have an ion and an electron in the final state. This can be elastic scattering, this can be inelastic scattering, many things can happen, that is a matter of detail. But you can get the same final state in which you have an electron and an ion in the final state with totally different ingredients, namely a photon and a neutral atom, which is what happens in photoionization. The ingredients of this pink track of scattering are completely different from the ingredients of this blue track. Here the initial state has got a photon and a neutral atom, here the initial state has got an electron and an ion. But the final state, when this photon is absorbed, you have a residual ion and then an electron is knocked out of the atom. So, the final states are exactly the same. So, we are going to study what is the relationship between these two processes. One is quantum collision, the other belongs typically to what we call as spectroscopy, and technically from the point of view of quantum processes, the two are complementary branches of the same physics, and collision and spectroscopy are not really two different topics, but two aspects of the same topic. And my attention to this was first drawn by the works of Walter Johnson and Lee, which came out of some earlier studies by Liu and Lee, and of course there are excellent contributions by one of the greatest contributors to atomic physics, which is Ugo Fano. Fano and his students, in particular Ravi Rao, who some of you know very well. So, there is a relationship between these two phenomena, electron ion collisions and photoionization, and there is a difference, and that difference is highlighted in the lower figure over here. So, look at the first block over here. You have got an incident plane wave. So, you have got a target and these are projectiles. You are considering a quantum collision phenomenon, and this electron beam or whatever be your projectiles, they come and impinge on the target and get scattered in various directions. It is not necessarily isotropic. The scattering amplitude depends on the angles and so on. So, that is again a matter of detail, but what this represents is that you have a plane wave which is more or less monochromatic, and then it gets scattered in all directions. So, this is the typical scattering phenomenon, which is what you study in a course on quantum collision physics. On the completely right side, just look at the plane wave which is coming out, this one. This is the photoelectron. It represents the photoelectron which is knocked out of the atom, and this atom really did not have a free electron in the initial state as existed in the electron ion collision process. This electron was actually born when the photon was absorbed. It did not even exist as a free particle, and the situation is somewhat similar to what one knows of the beta decay. The electron does not exist as a free electron inside the nucleus, but it is born in a certain radioactive process. Okay, so this electron, in that sense, this is not born out of the nucleus, it is born out of the atom, but it is an integral part of the atom, and the atom absorbs this photon and the electron is born. So, this is the photoelectron now. It did not exist earlier, and you can at best pretend its existence by spherically converging waves, electron waves, such that the flux from opposite sides cancels each other. The cancellation is an indication of the fact that it did not exist, but you can represent it by spherical ingoing waves which cancel each other in your mathematical model. So, that is what we are going to do eventually. And you can, this is the question that we just answered, where was the photoelectron for t less than 0? It did not exist as a free particle, but you represent it by spherically converging ingoing waves which converge to the center, and the flux from opposite sides of the sphere on all sides cancels each other, confirming that it did not exist. So, there is no net flux initially, and you can see that the picture that you have over here, which is now what we will use to represent photoionization, and this picture to represent electron ion collisions, we will ask what is the relationship between solutions to the quantum equation, which is the Schrodinger equation. How are these solutions related to each other? What will be of importance to us is that if you consider the electron ion collision, which is the process on the left, which is a very physical thing happening, you can talk about the incident projectiles getting sort of caught up in the interaction region for a while before it escapes where it is eventually detected. So, in a scattering experiment, where it is detected is what you call as the asymptotic region, r tending to infinity. It is just a few centimeters or a few meters away in your laboratory apparatus, which is sitting on your laboratory table, but it is far enough from the table to use r tending to infinity approximation. So, that is the asymptotic approximation, and you detect the particles, but these particles appear to have been delayed at the detector because they are spending a little bit of time in the engagement with the target in the reaction zone. So, there is a little bit of delay, and in today's class, which is our first lecture today, I will discuss about this time delay in scattering. Subsequently, and this might come in tomorrow's class rather than in the next class today, we will talk about how these solutions are related to the solutions of photoionization. Okay, so there is a certain symmetry that you can see from the picture, and the symmetry is time reversal symmetry, but we need to do this very carefully because time reversal has a very different meaning in quantum mechanics than what it has in classical physics. So, we will discuss the time reversal symmetry operator, its consequences, its properties. So, this is going to be a discussion basically on quantum mechanics and quantum collision physics, and then it all comes together to see how it translates into very exciting applications of attosecond pulses, because you are able to measure the attosecond time delay in photoionization process using the mathematical machinery we are building it from quantum mechanics and quantum collision physics. So, that is the course of our discussion for the next 2 classes today and 2 classes tomorrow. So, the focus today is on collisions, and here you have a collimator, you have got a wave packet which can impinge on a target either head on or at an impact parameter b, okay. And then it has got a certain longitudinal width as well, and you can represent the incident packet as a superposition of various momentum states. So, very often when we develop the basic formulae for quantum collisions and expression for the scattering amplitude, we consider strictly monochromatic waves, which is of course an idealization. What we are considering here is a more appropriate description of an incident beam, which is a superposition of various momentum states or various energy states correspondingly. The integral over momentum is over the entire momentum space as is written over here, but in practical terms, if it is nearly monochromatic, it might be over a small width delta k rather than the entire momentum space. If the wave packet is incident at a slight distance away from the central symmetry, from the axis of collisions at an impact parameter b, then this r will be replaced by r minus b, and that describes the wave packet with a subscript b corresponding to a wave packet which is not hitting head on, but slightly displaced, but it is still going to interact, it is still going to get scattered, and it is still going to get delayed as a result of its interaction. So, here we have this amplitude which is complex. I separate the magnitude and the phase over here. Any complex number you can write in polar form. Okay. So, I have the magnitude over here and the phase over here, which I stick in here. We can now look at this. You can combine all of these phases. There is a phase here, a phase here, and a phase here. You combine these three to get a beta, okay, and then you have got an amplitude modulus AK, and you can determine this from the form of the wave packet at the original time t equal to 0, because if you just put t equal to 0, so this e to the minus I omega t term will be unity for t equal to 0, and the rest of the terms will give you this AK, which is the transform of the incident wave at t equal to 0. So, from the form of the wave packet at t equal to 0, you can determine AK, all right. So, we are good with this. Now, let us take this forward. Now, what is interesting is that we have got oscillatory terms, and these are sine and cosine functions. And if you have a large number of sine and cosine functions which are superposed, means this is an integral which is nothing but a superposition, it is an addition of all these terms, and you have got the sine and the cosine waves, and in the asymptotic region, even if r changes very slightly, the sine kr and cosine kr will change in response to that, and if it is in this part of the sine, it will be shifted somewhere else, and these terms will cancel each other. You get it, everybody? So, the sine and the cosine terms, the oscillatory terms, will mutually destroy each other, and there will be nothing to worry about. Okay. However, the cancellation has to be dealt with very carefully. You have got the cancellation is happening also because the individual waves are moving at a phase velocity which is different from the group velocity. So, the wave packet moves at a certain velocity which is different in general from the phase velocity, and it is the gradient of the dispersion, the k dependence of the frequency is omega, which gives you the group velocity d omega by dk. These are typically normalized. We will begin with normalized states, and now we look at the oscillations which would destroy each other, and I caution that we have to consider this very carefully, because the mutual destruction will not occur if the overall phase, this beta, which is the sum of these angles which we discussed on the previous slide, if this beta does not change very much with respect to k, then there will be no cancellation, otherwise there will be cancellation. So, for us to talk about the collision dynamics, we are looking at a subset of situations in which beta is not changing very much with respect to k, and we now ask the question, when would this happen? What is the condition for this? What is the condition that beta does not change very much with respect to k, and it is obviously that the gradient of beta is equal to 0, okay, because it is the gradient of beta which represents the variation in beta with respect to the momentum. So, this must go to 0, and let us write this in one dimension. It is easier to discuss it in one dimension. So, gradient of beta equal to 0 is equivalent to d beta by dk at a certain, this derivative is to be taken at a certain value of momentum in the incident beam. And what is this? This d beta by dk you get by taking the derivative of this equation beta with respect to k. So, this is kz, k dot r, I am using the spherical polar coordinates. So, r cosine theta, the direction of the incident beam is what I consider to be the z axis. So, most of these things are self explanatory for those of you who are familiar with spherical polar coordinates and usual terminology of collision physics, which I will use with no hesitation, but if any one of you has a question, please ask. So, this is r cos theta, which is kz, its derivative with respect to k is z. So, this is the derivative coming from here. Then you have d omega by dk multiplied by t, and then you have d alpha by dk. Now, if you look at this relation, you can get z because it is the sum of these three terms which goes to 0. So, z itself is given by the negative of this term and the positive of this term. Okay. So, you just bring those two terms to the other side, and this equation would be familiar to you. So, this is in one dimension, this is the corresponding relation in 3 dimension. I replace the d alpha by dk by the gradient of alpha, and this is the derivative with respect to k. It is the gradient, but this is the gradient in the momentum space, remember that. And this relation is obviously familiar to you because it is nothing like what, it is nothing but what you see in kinematic equations in high school mechanics. So, it is just an equation corresponding to r at position at time t is equal to r0 times the velocity times the time difference, it is nothing but that. Where you identify r0 with the gradient of alpha and vi with the gradient of omega. So, now let us determine these quantities. If you take these gradients in the vicinity of some mean incident wave vector ki, then the expansion and expand alpha k about this mean vector ki. So, the first order correction will be the gradient of alpha times the scalar product with the difference in the momentum space, and then you will have higher order terms. So, this is like expansion of any function. You have a similar expansion for the dispersion for the k dependence of omega. I have written the first order term explicitly, and then you also have the second order terms, which I represent only by dot dot dot, but it does not mean that they are not there. Means as and when required we must address those terms. So, this is the condition that the oscillatory terms in the wave packet will not destroy each other. The condition is gradient of beta equal to 0, and these are the expansions of alpha and omega, and now we seek what these gradients are. So, omega is nothing but E over h cross, E is p square over 2m. So, it is h cross square k square over 2m, and this h cross comes from here. So, omega is h cross over 2m k square. Are we all together? And now we want the gradient of this. So, we need the derivative of k square with respect to k. So, you will get h cross k over m, that is the velocity. Okay, so, we get the velocity term over here, and we get since this velocity appears over here in the expansion for omega, we can plug this velocity h cross k I over m over here in the expansion for omega. Good. So, this is what we are working with. We have put this velocity over here in the expression. Now, we are writing this omega explicitly in terms of this power series expansion. We are writing this alpha also explicitly in this power series expansion. Higher order terms continue to be denoted by these dots. And now, in terms of this, our incident wave packet is now written in terms of these terms, and we can do some rearrangement over here. And this is nothing but organization of some terms which is a little easier to handle, no big physics in it and no big mathematics in it. So, you can work this out yourself. I will share the PDF with you, okay? Except that one can always make a careless mistake, and I do that very often. So, I lose terms and then spend half my life searching for those. So, anyhow, so here we are. We have got this rearrangement of terms, and there are certain terms which have nothing to do with k, and they can be pulled out, like ki, it is the momentum at a particular momentum, right. So, that need not stay under the integration sign. So, all those terms with ki, r0 is also a constant, it has nothing to do with the integration in the momentum space. So, all of these terms I pull out, and the rest of the terms are there under the integral, which really depend on k. Okay. So, it is just very straightforward manipulation of terms. Then again, you have got terms which is just a phase. There is no other information in this term other than what is there in the phase. These are, it can be absorbed in the overall constant of normalization, which is some complex number. So, it being not consequential, you can ignore it. Effectively, you are absorbing it in what will be an eventual constant, because any wave function which is multiplied by any complex number is also a solution to the differential equation. So, no big deal about it. Okay. So, we write this term without these inconsequential terms, just so that we have to write lesser. What took 2 lines now takes only 1 line, is the same thing, in which I have dropped the inconsequential terms. And what we have is this relationship in which I have now combined these phases, this term and this term, into a common one over here. I have dealt with these things in some detail in my book in chapter 10. This is equation 102 in this chapter. So, you can also go through that for some details if you want to, if you miss anything. And here, what is this? This is e to the minus I theta times e to the plus I theta. So, it is basically 1. So, I just multiply by 1, I can always do that. I multiply and divide by this term effectively, by this phase, and I rewrite this term which is written over here, and then I take it to the top of the next slide. Are we together, everybody? And now we notice that there is a k dot r minus r0 minus vit term. So, if you look at this term, it is like the wave packet, but at a different position at a later time t. So, it is very reminiscent of the effect you have in classical kinematics, that you throw a stone and its position later will depend on the velocity at which it is thrown, the initial position and so on. So, nothing more than that. And all this is fine, but there were some terms which I had represented by these dots. We dealt with only the first order linear terms, and all this is fine provided the second order terms and higher order terms can in fact be neglected. We did not check it, we are going to do that check now. So, we will now look at the second order terms. So, the second order term typically means, let us take d2 omega by dk2, and then there is the square of the displacement in momentum space, and you can write this, and we are asking if this is ignorable. In other words, we ask if this term is much less compared to 1 in our system of units. It is equivalent to asking if the second order terms are ignorable in our set of units. Now, this question boils down to asking, I keep h cross over m over here, this is delta k. So, delta k square into t, is this equal to 1? If the answer is yes, then sure we can ignore the terms. If it is no, then we cannot.